Welcome to the next talk. I'm going to be talking about Kinarm Lab peripherals and how you can interface with them. I'll talk a little bit more about position control, which I touched on yesterday, and then going to end off with a couple of sort of tips and tricks on programming best practices. I'm going to start with what I refer to as integrated peripherals. And what we mean by that are optional modules that you can buy from us, but they're managed and their calibration is all integrated within Dexterity. It's all within that one user interface. The types that I'm talking about are the gaze tracker, force torque sensors, force plates, and height sensor. And I'm just going to go through each of those in a little bit more detail. The Kinarm Gaze Tracker is an option that's available for both platforms, our Exoskeleton and Endpoint Lab. And it, of course, provides the position of the subject's gaze. So you can see in the image here, there's a gaze tracker, there's a camera, there's an illuminator. This all is in the infrared spectrum. And the camera actually looks up at a reflection in this top mirror, which then bounces down off of this mirror back over to where the subject's face would be over here. And it's fully integrated. It runs in real time. All the data is collected by the robot computer and is available in real time to be able to not only record where your subject's looking, but you can use that information to drive the system behavior. So you could have targets move when the subject looks at them, for example. Force torque sensors are something that is available only for the Endpoint Lab, and they are located here. So they're between the handle that the subject grabs and the end link of the robot, and it provides a measure of both the force and the torques by the subject that are applied by the subject to the handle. So we have forces, of course, in all three dimensions, X, Y, and Z, and then torques are just about the X and Y. The handle spins, so of course there's no Z torque there. Again, the information that is recorded by these force torque sensors, it's all recorded for your data files later, but because it's all fully integrated and accessible in real time, you can use this to drive system behavior. And the force plates is the last integrated option that I'm going to talk about. And the idea here is it's for posture measurement. So you can see over on the right, there are the force plates embedded in the floor. This is obviously available only for the Endpoint Lab with our what we call adjustable height configuration, where this whole system goes up and down to adjust to the height. Force plates measure what we call ground reaction forces and moments for each foot. So again, this is important for being able to measure posture. Like the other peripherals, this data is available in real time, so you can not only use it for analysis after your experiment, but you can also use it to drive system behavior. All of these units are connected to the Kinarm Lab in the same manner. So here are those three options that I talked about: the gaze tracker, the force plates, and the force torque sensors. And all of them actually connect to the robot computer via a network switch. So this is the dedicated Dexterity LAN, and the information is streamed using a protocol called UDP. What can we do with this? I mentioned that you can use this to drive system behavior, and I'll give an example of gaze position. Let's suppose that you wanted to use gaze position to do something. Obviously, you need to somehow access it. And if you go within your Simulink library browser and you click within the Simulink library, there is a sub-library called signal routing, and we can drag this from block over. And this allows us to access signals that we provide. And if I double click on that from block, it opens up this dialog. And then from the drop-down menu, you can select one of these signals that we've generated called Gaze Global. And then suddenly we have access to information. So how do I know what's in Gaze Global? Well, this is where you would go to our Creating Task Programs guide and look up all the various from tags, and you can see, well, what information is available there. This is the approach that you would take with the force torque sensors and also with the force plates. It's the same idea. Now, one of the things you'll notice is that Gaze Global contains 3 pieces of information: the X position, the Y position, and a timestamp. So why do peripheral data have timestamps? I mean, this information, it's being collected by the robot computer. We know when it arrived. Well, it turns out what those timestamps are is that's the timestamp of when that data was recorded by the peripheral. And this is important if you want to calculate the derivatives of the data. Let me walk you through what I mean. This is the timestamp by the peripheral. So for example, the gaze tracker. So it records data at this consistent rate of time. There is a little bit of variability in the transmission over to the robot computer. And so what can happen is that when that data gets logged by the robot computer, so this is now the dexterity timestamp, or if you're looking at your data file, really this is the frame index, you can get data then logged at these times. So these 4 pieces of data that actually were collected at a consistent time rate end up showing up having a little bit of jitter when you look at the actual data file in our records. So again, DT might be constant on the peripheral, but not constant when it's actually logged by the data. If I look at just gaze position, it doesn't really make much difference. I mean, if I filter things, this would all smooth out and this would be almost identical. But if I'm going to look at a derivative like velocity, suddenly I've got problems. Because if I use the dexterity timestamp, so if I'm doing a velocity equals delta x over delta t, if I use the incorrect delta t, I can get this huge noise, which is all just basically quantization error coming up, which is not really in the signal. So moral of the story, if you want to calculate a derivative of one of these integrated peripherals, make sure you look at the timestamps from the peripheral. It's also possible to integrate a number of or all sorts of different types of peripherals that we talk about in terms of or refer to as non-integrated. And what I really mean is that they're not going to be managed or calibrated through dexterity. So the data is still timestamped, so it's still time synchronized with the rest of the Kinarm Lab, but we don't build up any sort of functionality to manage the calibration of it because we don't know anything about it. It's outside of what we provide. And there's a number of different ways that you can interface with some sort of non-integrated peripheral. The most common is through analog inputs and outputs. Most of the Kinarm Labs we sell come with these optional analog inputs and outputs, and those just take plus or minus 5 volt or send out plus or minus 5 volt signals. And so that allows a very simple standard interface with other technologies. Digital inputs and outputs are effectively the same in terms of being very generic for an interface. You can also interface over a network. So this is the same way that we have chosen to manage our integrated peripherals. We connect things via the Dexterity LAN and using a UDP, which is a network protocol. And we've had customers who wanted to interface, for example, with another computer that was perhaps recording some other information. Well, how do we actually do this? Analog inputs can be accessed using the following approach. If you go to the Simulink library browser and you look in the Dexterity library, you click on the Kinarm input-output sublibrary, and you'll see that there's an analog inputs block that you can just drag into your model. If you were to double-click on the dialog here, you can select which channels you're going to look at, and they all pop out here, and your data is available. It's just right there, and then you can do whatever you want with it. Of course, recognizing that this is going to be a plus or minus 5 volt signal. Only you know what that 5 volt signal means because it could be coming from a potentiometer measuring some angle or some other piece of equipment. So it's a very standard block. Analog outputs are also quite similar. We don't have any specific block in our library, so you'll have to go to the Simulink real-time library, go to the D to A, so digital to analog output sub-library, and the cards that people have these days are the National Instruments M series 6229, and then you just, again, take that block, drag it into your model, and you can then put any voltage or any signal that you put in there will produce a voltage output. So for example, one of the things that we've had a number of customers want to do is they want to play sounds. So of course, sounds is it requires a continuous waveform. What you do then is you would connect some sort of standard computer speakers to the BNC connector outputs. So these are the analog outputs on your D to A board. Find some wave file that you are interested in, and you can then downsample it to 4 kilohertz because, of course, the robot computer operates at 4 kilohertz. And then you can embed the waveform in your task and feed it to the analog output. There's a lot of little details to actually make that work, and so if you are interested in something like this, then I would send you over to our Kinarm support site where we've got some sample tasks which walks through all of these steps in terms of how you filter and downsample your waveform and embed it and use it in your task to produce a sound. One limitation I'll just point out, of course, is that since the robot computer is going at 4 kilohertz, that means your bandwidth is going to be just 4 kilohertz, which means you can only actually hear sounds up to 2 kilohertz. Digital input and output, very similar in the sense that there are just blocks that you drag from the standard Simulink real-time library. Again, this is the same card because these are National Instruments M series cards, the 6229. And so if you want an input, you just drag it in, and then suddenly you'll have access to signals coming in. If you wanted an output, then instead of the digital input library, you would go to the digital output library, find the analogous block, drag it into your model, and then whatever signal you feed into there, 0 or 1, would show up on your digital output as a 0 or 5 volt signal. If you want to communicate to another computer, at one level it's quite simple, but it's actually, there's a lot of details, and in this case, the devil is in the details in terms of making it work. But you would use this protocol called UDP. So an example that we've had a number of customers do is the customers who are, say, have neural recordings from a non-human primate, and they have their neural recording system is recording from some 128 channel array at some, fantastically fast data rate, and it's doing real-time processing to try to come up with some sort of, aggregate signal. And then they want to take that signal and use it to drive the, position or speed or something of the Kinarm robot. So what you have to do is that on your external system, you have to, figure out what signal it is you want to do, write some code to send out a UDP packet. And on our side, on the Kinarm side, you again go to the Simulink real-time library, go down to these UDP blocks, drag them in, and provide a little bit of information in the dialogues here to be able to pull out those packets. And then, of course, you need to know how to interpret the bytes that come out of that. And since you will have written the packet encoding on the other side, you would know this. But again, there's a fair bit of detail in terms of actually getting that to work, but it's all available for you as an option. I'm going to flip over now and talk a little bit more about position control. I touched on it briefly, and I'm going to emphasize once again this, although this is something that lots of people really want to do, it is definitely more advanced than doing things like applying a torque perturbation. Well, what is position control? And it's important to understand that at its most basic level, it's really a very stiff spring. It's a stiff spring between some desired position and your actual position. So in this case, imagine that the desired position is this red dot. If your actual position, the fingertip is some distance away, then there'll be a spring that tries to pull you into that dot. And you can imagine that the stiffer that spring is, as it becomes really stiff, then the fingertip is going to spend more and more of its time really close to the dot. You cannot have something that's infinitely stiff, so it can't be perfect, but it ends up being really close. For those of you who are familiar with PID control, there is a little bit more detail than that, but I am just going to keep it simple because this is the most important part, is understanding that it mostly is about a spring. But there's something that's important then to understand, which is when you turn on position control, what's going to happen? Well, if you turn it on, because force equals negative kx for a spring, if you turn on the position controller when x is not equal to 0, then that means your force is going to go from 0 up to some non-zero value instantly. So if my desired position was at this location here and I turned on the position controller, boom, there's going to be a big force suddenly applied that's going to feel like a big torque perturbation or force perturbation to your subject. Maybe that's what you want, but most often with the position control, that's not what you want. You're not trying to give perturbations to people. Well, how do we turn on a position controller then? There's a couple different options that you can take to avoid this initial perturbation. And one is you just ramp on the position controller slowly. So instead of just turning it on so that force equals negative kx, you can add some sort of scaling factor so that over some time period, say half a second or a second, it scales up from 0% to 100%. Another option is that you only turn it on with x equals to 0. Well, how do you do that? Well, what you do is you set the desired position equal to the actual current hand position. And if you do that, then x equals 0 and you turn it on, the subject won't even notice because there's no force. They'll notice as soon as they start trying to move, but they won't notice when you actually turn it on. So how do we move? How do we create trajectories? And it's important to know that you want to change the desired position slowly. So if I start at some nominal position and I change x instantly, that's going to result in an instant change of force. So if I do that, if I move the position, if I jump it from that initial position to this next position, again, because force equals negative kx, that means my force profile is going to follow that same position profile in time. It's going to be a step change, which again, usually that's not what people want. So what you need to do, if you want a smooth trajectory, so if you want that position of the person to follow a nice smooth trajectory from one point to the next point, then what you need to do is change that desired position gradually. You started at one point, and then over some time period, whatever trajectory duration you're interested in, you just slowly update the position. And then what's going to happen is the person's hand is going to get pulled along. Now, if we create this kind of trajectory, it's important that that trajectory actually be smooth. And the reason is because, again, there's a few more details about position control. It's more than just a spring. All right, the feedback part of the control is, again, mostly a spring. So that's always there. But one of the downsides of a spring is that it acts with a bit of a delay. So if the position moves, then there's a bit of a time before the subject's hand is going to follow it because they have to respond to that. Our position controller has a built-in feed forward as well, a bit of a feed forward model. And what that does is that predicts what the required force is going to be based on the system inertia and the desired trajectory acceleration. So this is optional, but it does improve the response to the desired changes because there's no delay in the feedback. However, acceleration is the second derivative of position. So if your desired trajectory has some sort of noise in it, if you take a second derivative of it, that is going to get amplified, which means that you'll have a very noisy acceleration, which means that you'll have very noisy feed-forward forces, which your subject's going to end up seeing. So the solution is when you're starting to implement position controllers, I'd start off by turning the feed-forward off to make sure that everything else is working. All right, it's always important to, if the system isn't working, how do you track down a problem? Well, let's simplify things. So in this case, you turn off the feed-forward control when first testing your position controller to make sure that everything else in your code is working. Are you turning it on correctly? Are you moving and changing the desired position in the way you want? Get all of that sorted out first, and then you can turn the feed-forward back on to get the better performance. And you can, if a problem appears then, well, then we know exactly where that problem is coming from, and it has to do with noise in your desired position. So that's a lot of information, but we do want to try to make people's lives a little bit easier. And so there are 2 sample tasks on the Kinarm support site. Each one tries to use or does use the position controller in a different manner. So there's no right one to use. It's just they do things. They're trying to solve different problems. So you choose one that's closer to whatever you need and start with that because it works. And then you can go and modify it sort of step by step to make it do what you want to do, and that'll get you to your end goal much more quickly. I mean, in truth, this is just a general approach that's always good. We have lots of different sample tasks on our website. There's no point in, starting from scratch and recreating the wheel. Go look at what other people have done, how they've solved a problem, and start from there. This is something that's been touched on a couple times now, but again, just to sort of remind people that if you want to do something that's similar to something that we've done, well, start with one of our blocks and then modify it. And the key feature, of course, is that you have to disable it. You have to unlink it from our library. If you try to update what's in our library, then the problem is any other tasks that use the library will unfortunately then use your new modified code. And then when we update new versions of Dexterity, there could be incompatibilities. So you need to unlink it. If you right click on the block, go down to library link and choose disable link, that will then unlink it from our library. And then you can go and customize it to do whatever it is you need to do. I have a few more slides and I'll try to go through them reasonably quickly because I know you can all read, and so you don't need me to spell out everything, but just it's worthwhile. Spend some time looking at these, particularly if you're sort of new to programming, to get some ideas on things that are going to make your life easier. So for example, we like to use all caps for constant names, and so it's nice to have a consistent naming convention. I always like to choose names that are meaningful, so later on I come back to the code, I have an idea of what that variable does. I add version names to all of my task programs and protocols because that way I can follow the history and I know, oh, this one was done before that one. Much easier when you're trying to go back. Try to avoid using sort of magic numbers. I mean, if you put a number in there and it is there for some meaning, then create a constant so again you can know what that number is and where it came from. Specific things for us is to use lots of event codes. As I think some of you have heard before, and when you start going to try to run your task on a Kinarm, it's really, really helpful to use event codes to sort of debug and verify that things are working the way you want. Scopes we've mentioned are really useful for tracking down bugs and errors and unexpected behavior. This is a cool thing, is that when you write MATLAB code, so you write some embedded MATLAB code in your model, it's MATLAB code. And so one way to troubleshoot it is you can actually just take it out, put it in MATLAB, and maybe create, might need to create another little function to help sort of test it, but it is MATLAB code and you can run MATLAB code in MATLAB. And so that's a potential useful way for when your MATLAB code gets complicated to test it out. Another thing we showed in a couple examples, it's always good to have timeouts so that your experiment doesn't ever get stuck in an impossible state. Again, talking about event codes here, but more in the context of it makes your analysis post-experiment potentially a lot easier. Just a general thing, don't repeat MATLAB code, use loops, methods, functions, etc. Take care with units. Some people prefer SI units, some people prefer millimeters, some people prefer centimeters. Just be consistent or provide some information so you know what your units are. And we're a big fan of using the global coordinate system rather than local coordinate systems. Save early, save often, back up. Particularly when you get to a stage where something's working, you got one little part of your task working, save that and then start using a new version, because then you can go back if you have problems and things stop working. Lots of, MATLAB, it is amazing how much information is out on MATLAB in terms of other people trying to solve problems. That's a fantastic resource. Google, of course, has lots of stuff if you're interested in, say, trying to figure out some math, like those cool spirograph functions that Ethan was talking about earlier. Lots of comments in your code. This will only become relevant to you when you go and look at your code 6 months from now and you wonder what it was you did and why. And of course, as with any problem solving, start simple. Just change one thing at a time, make sure it works. And last, verify your code. The fact that your code compiles, that's great. The fact that it can run on the Kinarm, that's great. Doesn't mean it actually does what you want it to do. So always take lots of time and care to verify that, because you don't want to collect 6 months of data and then discover there was a bug.